Hello everyone, this is Chandan Jha and in this video I am going to discuss limits in calculus. So without any delay, let us start the video. So to understand limit, let us consider a function fx which is defined in an interval that contains c except possibly at x equals to c. That means the function may or may not be defined at x equals to c, but it is defined in an interval that contains c. Let us also consider delta and epsilon greater than 0, which are infinitesimally small. That means their values are almost 0 but not 0. Now let us see the Cartesian plane related to this function fx. If this blue curve indicates the function fx and here this point c and this point L, that is corresponding value of fx at x equals to c. Let us also indicate this vertical line as c minus delta and this right hand side vertical line as c plus delta. Now for the limit, we have to understand that for any value of x that will lie between c minus delta and c plus delta, we shall get a corresponding value of fx that will lie between L minus epsilon and L plus epsilon. If such condition occurs, then we say limit of fx at x tends to c is equals to L. That means for any value of x that lie between c minus delta and c plus delta, that means the values of x are very nearer to c, and for those value of x, if fx will lie between L minus epsilon and L plus epsilon, then limit of fx at x tends to c will be L. For example, if c is 1 and delta is 0.00015, see it is almost 0 but not 0. So now you can understand that the values of x will be how much nearer to 1. And for those value of x, when we get fx, that will lie in between these intervals L minus epsilon and L plus epsilon, where the value of epsilon is also similar to delta, that is almost 0 but not 0. And one more thing to remember, these values of epsilon and delta are correlated. For a different value of epsilon, we shall get different value of delta. Now, if such condition occur, then we say limit of fx at x tends to c is equals to L. So, when we say limit of fx at x tends to a is equals to L, that means for all x lie between the interval a minus delta and a plus delta, f of x will lie between L minus epsilon and L plus epsilon, where delta and epsilon are correlated. So in other words, limit of fx at x tends to c is equals to L means that if and only if for every epsilon greater than 0, there exists delta greater than 0. As I have already said, this epsilon and delta are correlated. That is why this condition will occur if and only if for every epsilon greater than 0, there exists delta greater than 0 such that f of x minus L is less than epsilon. This indicates this function, the value of function, and this limit L, their difference will be very less, that is almost 0 but not 0. They are very nearer to each other whenever 0 is less than mod of x minus c less than delta. That means the value of x and c will also be very nearer to each other such that their difference will be less than delta. Let us understand with one example. So we are considering fx is equals to x square minus 1 by x minus 1, and we need to find out limit of fx at x tends to 1. So if we consider x equals to 1, then we shall get f of x as 0 by 0, that is undefined. So as we have already discussed that at this point the function may or may not be defined, but its limit may exist. So if we get closer and closer to 1, then we can get some value for fx. Let us have a look in this table. Here you could see that we have considered the value of x as 0.5, 0.9, 0.99, 0.999 and so on. And these values are nearer to 1 but not 1. And for those value of x, we are getting corresponding value of fx by simple calculation. And as we are approaching towards 1, the value of fx is also approaching towards 2, that is 1.9999 for x equals to 0.9999, and you could see that all the values of x here are in the left hand side of 1, and thus we say it as left hand limit of fx. So, and we write it as limit of fx at x tends to 1 minus, because all the values of x lie in the left hand side of 1. Similarly, in the right hand side of 1, the values are like 1.5 or 1.1 or 1.01, 1.001 and so on. And you could see as we are approaching towards 1, the value of fx is also approaching towards 2. So for 1.00001, the value of fx is 2.00001. So you could see the difference between this value of x and 1. It is almost 0 but not 0, and hence we are getting a value for this function x fx. Now here you could also observe that all the values of x are in the right hand side of 1. Thus we call it as right hand limit of fx, and we write it as limit of fx at x tends to 1 plus. Now from the above tables we can get limit of fx at x tends to 1 minus as 1.99999, and limit of fx at x tends to 1 plus, that is right hand limit, as 2.0001. Now both the values are almost equal, that is 2, and hence we can write limit of fx at x tends to 1 plus is equals to limit of fx at x tends to 1 minus is equals to 2. So geometrically, if we see in the Cartesian plane, here at 1 the function is not defined, so I have indicated a break here. But when we draw the vertical lines in left hand side and right hand side of 1, that indicated by 0.99999 and 1.0001 respectively, we get a corresponding values of fx here as 1.999 and 2.0001. Those values are nearer to 2, and hence we say that limit of fx at x tends to 1 is equals to 2. Now one very important thing to remember, that limit at a point exists if and only if left hand limit will be equals to right hand limit, then only limit at a point will exist. And we can say that limit of fx at x tends to c plus is equals to limit of fx at x tends to c minus. If such condition occur, then only limit will be existing at that particular point. So let us work with one more example where we can see that limit will not exist at a particular point. So let us consider the function fx as mod of x by x, and we need to calculate its limit at x tends to 0. Now, if x is greater than 0, that means if x is any positive value, then this mod x will remain as x, because the work of modulus function is to produce a positive result. And here we are already considering a positive value of x, that is x is greater than 0. Then mod of x will remain as x. For example, if x is 2, then mod of x is also 2. So f of x will become x by x, and that is equals to 1. And since all the values are greater than 0, that is in the right hand side of the 0, then we can write limit of fx at x tends to 0 plus is equals to x by x, and that is 1. Now let us have a look in the left hand side limit. So if x is less than 0, then mod of x will become minus x. Let us see how. When we are considering a negative value of x, then mod of x will make it positive, and mod of x will make it positive by multiplying it by minus 1. For example, if x is minus 7, then for mod x, this minus 7 will become 7, and that minus 7 will become 7 if we multiply minus 1 with this. Thus, mod of minus 7 is minus of minus 7 is equals to 7. So that is why we are writing mod of x is equals to minus x when x is less than 0, when x is negative number. Thus, f of x is equals to minus x by x, and that is minus 1. So left hand limit of fx is minus 1. So here we are getting that limit of fx at x tends to 0 minus, that is left hand limit, is not equals to limit of fx at x tends to 0 plus, that is right hand limit. Therefore, limit of fx does not exist at x equals to 0. So we need to remember that limit of fx exists if and only if following condition will be satisfied by a function at a. That limit of fx at x tends to a minus will be equals to limit of fx at x tends to a plus should be equal, should have the same value. If both the values are L, then we say limit of fx at x tends to a is equals to L. So that's all in this video. Thank you for watching.